Although recursion can simplify some problems, it can also produce inefficient solutions. Let's examine when using recursion is best and how to measure its efficiency. But first, let's consider the relationship between stacks and recursion and what it tells us about which problems are best suited for a recursive implementation. Every recursive program implicitly makes use of the compiler's runtime stack. This stack is used to store all local variables, parameters, and the return address of every method. Consequently, any problem that can be solved with recursion can be solved with iteration and may require the use of an explicit stack. Recursion is especially useful in simplifying problems that cannot be solved in constant memory. Such harder problems, ones that can't be solved in constant memory, generally require the explicit use of a stack or some equivalent data structure when solved using iteration. One of our implementations for counting the terms of the Fibonacci sequence illustrated the possibility that recursive solutions can be very inefficient. So now let's consider the general characteristics of such problems. One clear indicator that a recursive implementation will be inefficient is when it involves duplication of work. Clearly, duplicating any computations is undesirable. It is sometimes possible to rewrite such solutions recursively without duplication using tail recursion. It may require the introduction of additional parameters and a helper method to start the recursion. Dynamic programming is a technique that saves intermediate results, which avoids the duplication of work and can eliminate the inefficiency. Dynamic programming solutions often replace recursion with iteration, but it is also possible to still use recursion as long as the intermediate results are saved. The term memoization is often used to describe the process of saving those intermediate results. Next, let's consider the characteristics of problems that make them ideal for a recursive solution. As we mentioned earlier in the discussion of how stacks and recursion are related, recursion works best on problems that cannot be solved with constant memory. As an example, consider the problem of reversing the numbers contained in an input file. To reverse such a list of numbers, they first need to be read into memory. No matter how large a fixed size array was allocated, there will always be an input file with more elements. Another example is the evaluation of expressions. It is an example of processing a nested structure. In the same way that an input file in the previous example can be of any length, there is no bound to how deeply an expression can be nested. The deeper the nesting, the greater the need for saving intermediate results. If either of the previous examples were implemented with iteration, using an explicit stack would be ideal, which is why such problems are ones that lend themselves to recursion. The most effective use of recursion involves programs that are not tail recursive. Recursion is most effective when some action occurs both before and after the recursive call. Although it is true that tail recursive solutions may be efficient because compilers can easily translate them into using iteration, the best uses of recursion are ones that are both effective and efficient. Now that we have discussed the characteristics of programs that use recursion, both inefficiently and efficiently, let's see what techniques can be used to measure that efficiency. We begin with the simplest case, recursive methods that have no loops, which means a single activation executes in constant time. In that case, the execution time is proportional to the number of nodes in the activation tree of the recursive calls to the method. So if we can determine a function that counts the number of nodes of that tree, given some value n, that function's growth rate will describe its efficiency. Its memory usage will be proportional to the height of the activation tree, because each activation along the longest branch will require space on the compiler's runtime stack for its activation record. As a result, recursive methods never have constant memory usage. This fact is another way of saying that any problem that can be solved with constant memory is probably not one that can make effective use of recursion. The reason is that recursive methods always use memory on the compiler's runtime stack. Finally, we consider a more general method of determining the efficiency of recursive methods. This technique applies to methods that do have loops, as well as those that don't. This technique uses recurrence equations. A recurrence equation is the integral analog of differential equations. Like differential equations, to solve a recurrence equation, an initial condition is required. That initial condition would typically be something like t of 1 is 1. In addition, like differential equations, there is no general technique that works for solving them all. For our purposes, we are less concerned about the techniques for solving them and more interested in the ones that arise most often and knowing their solutions. So let's consider the most common ones. In this equation, the size of the data set is cut in half each time, which is indicated by n over 2, and the amount of work on a single activation is constant, which is represented by the addition of 1. This is the recurrence equation for a binary search. Its solution is log base 2 of n. In the next equation, the size of the data set is reduced by 1 each time, and the work on a single activation is constant. This is the recurrence equation for a linear search. Its solution is linear. Notice that that corresponds to the analysis that counted the lines of code. In the next example, the work on a single activation is not constant but linear. The data set size is reduced by 1 each time. This is the recurrence equation for some of the simple sorts, such as the insertion and selection sort. The solution to this equation is quadratic. Here the data set size is cut in half each time, but the work on each activation is linear. This describes some of the more complicated sorting algorithms, the merge sort and the quick sort. The solution to this recurrence equation is n log n. In this last one, when the size of the data set is reduced by 1, the amount of work doubles. This occurs when a method is doubly recursive. The addition of 1 reflects the constant work on a single activation. This is the equation for the most straightforward Fibonacci number solution, although in that case it does not quite double. Recall in that case the efficiency was exponential. When we study the previously mentioned algorithms, the efficiency analysis provided here will be used to determine their efficiency.